Hello, and welcome to Agrosive Physics. Today is day 85, and our topic of discussion today is resonance. Now, all objects vibrate at what we call their natural frequency. And a natural frequency is the frequency at which an object will vibrate. So resonance is when an object vibrates at its natural frequency because of a source that's producing the same frequency wave. For example, if you were to cook something in the microwave oven, microwaves happen to have the same frequency that water vibrates at. So water's natural frequency is the same as microwaves. So when you're using a microwave oven, what you're doing is using the microwaves to cause the water inside the food to vibrate. When the water inside the food vibrates, it increases its temperature and changes the average kinetic energy of the particles inside the food. You can't really cook food in a microwave that doesn't have any moisture in it. So the key to using a microwave is to have foods that have water inside of them. So it's typically used to reheat things that were already cooked, because then they're cooked and you're just bringing them to a higher temperature. On the other hand, if you try to cook things that are dry, you'll find that they don't really work well in a microwave itself. So the microwave has the same frequency that water vibrates, so when the microwaves are hitting the water molecules, it causes the water to vibrate. So the water is resonating because it has a natural frequency that's the same as microwaves. Now the key is that vibration will occur only when a source is producing the same note or the same frequency wave that the object will vibrate at. If a singer sings a very high note, that note may produce a resonant frequency that will cause crystal to break. However, glass of the same shape may not break at that same frequency. So crystal will have a natural frequency that's different than glass. Even if the glasses are identical in shape and size, crystal, if it's made out of crystal, that will cause the crystal to break. And on the other hand, a glass cup that's made of the same material may not break. Now what happens is when it starts to vibrate its natural frequency, the crystal goblet or glass will start to vibrate. Now if it vibrates more rapidly because it has the same frequency, it will cause the crystal to actually ebb and flow in a pattern that will look like a standing wave briefly, but ultimately the glass won't be able to handle it and the crystal will break itself. So at certain frequencies, you can actually have a singer or a note that's produced that can actually break a glass. Now, on the other hand, if someone's playing an instrument where there's glasses filled with water, they may rub their finger along the outside of the rim of the glass, and that vibration will cause a frequency to be produced that will be different notes. And you can play different notes depending upon how much water is placed inside of different size glasses or containers. So that is using the natural frequency of the glass in terms of the water that's inside the glass, and it will cause it to vibrate differently. But in each of these cases, you're trying to produce a note that will cause the other object to vibrate at whatever frequency it wants to vibrate. When you have a tuning fork, that vibrates at a single frequency. So if I were to take that tuning fork and vibrate it near a guitar string, if the guitar were in tune, it would cause that guitar string to actually start to vibrate itself. So you can use a manual tuning method rather than an electronic tuner to tune a guitar. The problem with that is that you would need 6 tuning forks to cause each string to vibrate its natural frequency, as opposed to having a tuner that may be electronic and all the different notes are stored electronically inside. Or you might have a pitch pipe type tuner where you play a note and then change the frequency of the guitar strings to match the note itself. So natural frequency could be an example of a tuning fork vibrating. When you cause it to vibrate, you can bring it near another tuning fork, and that tuning fork will start to vibrate. We call that sympathetic vibrations. And the alternative would be like in a microwave where you're using microwaves themselves that happen to have the same frequency that water vibrates. There's even an example of an engineering feat. A bridge was built in Tacoma, Washington in the 1940s where when the wind started blowing past it, because it moved down a gorge, of course there was a bridge to cover a gap in the earth, it caused the bridge to vibrate. So some people believe that vibration of the bridge was caused by resonance of the wind. Now there's still debate over what actually caused that disaster, but the effects of that light wind, there was 30-mile-an-hour winds, caused the bridge to vibrate so radically that it actually broke the concrete and steel and caused the bridge to collapse. So resonance can be blamed for that disaster, which happened over 70 years ago now. So resonance is when an object vibrates at its natural frequency. If you were to take another object and bring it near the original object and you had the same frequency, it would cause that second object to start to vibrate. We use that in microwaves to cook food or reheat food. We use that when we try to tune instruments in some cases if it's manually. Piano tuners may use actual tuning forks to tune the piano by causing the tuning fork to vibrate, which will cause a string to vibrate if it's in tune. So resonance is when a wave is formed that causes another object to start to vibrate because it's at its natural frequency. Now, we talked about before how resonance is the frequency at which an object will vibrate, and we have a certain frequency that most objects vibrate at, and it's called its natural frequency. Now, if we have a tuning fork on top of a sounding board, and we have these in the lab typically because then the sound waves can be amplified and sent in a single direction. So this is usually a box, and one end is open. So let's say this end is open, and this other end is closed. So when we hit the tuning fork, it's going to send a sound wave out in that direction. Now, if this is a 256 hertz tuning fork, we could set up another tuning fork here that happens to be 256 as well. And if we strike this one with a mallet, it will cause the air to vibrate. Now, because this tuning fork vibrates at the same frequency, it will resonate when it is hit by that same sound wave. So this will start to vibrate as well. And we call that sympathetic vibration. Now, this is the same principle that a microwave oven works on. What happens is the microwaves hit the food, and any moisture will start to vibrate because the microwaves vibrate at the same frequency that water vibrates. So the water will sympathetically start to vibrate, and all the water inside the food will start to vibrate faster. Now, as the average kinetic energy goes up, so will the temperature. So the temperature will increase. And that's why we can reheat food in a microwave oven. Now, if we put a dry food inside the microwave and we try to heat that, it's not going to heat up because there's no water that will start to resonate. So you need to have moisture inside the food already for a microwave to work. And that's because microwaves vibrate at the same frequency as water. So objects will vibrate at a certain frequency. We call that its natural frequency. And if we send a sound wave, or in this case light, that happens to have the same frequency, it will start to vibrate as well. We use this principle to tune guitars. When you get to a certain note, you'll cause the next string to vibrate because of resonance. So if you tune a guitar without an electric tuner, you can use resonance to do that. But the bottom line is objects vibrate at a certain frequency, and if they're hit with that same frequency, they will begin to vibrate sympathetically. So that's resonance.